Hi girls, how are you? So yesterday we started to look at dynamic equilibrium. We looked at some of the concepts involved in that. And today we're going to start to look at the sort of mathsy side of that, okay? And one of the things you're regularly asked to do is to calculate the value of Kc for a reaction, okay? So just before we do that, let's just go back over what exactly Kc is, right? So the best way of doing this is looking at an actual example. So the example I'm looking at is from 2008, and we're just going to look at part B of that today, okay? And in that, you're given this equation here. Hydrogen and iodine react to produce hydrogen iodide. I've written it out for you here. Again, this is in the question 2008, part B. You can find it yourself first and pause this if you want. And we're told it's a reversible reaction. So what that means is that hydrogen and iodine react together to produce hydrogen iodide, and then that hydrogen iodide reacts again to produce hydrogen iodine until a balance is formed between these two. And that the extent of that balance, whether there's more hydrogen iodine in the mixture or hydrogen and iodine in the mixture, depends on this value here, the value of Kc. And we talked, or I mentioned very briefly yesterday what that was. I didn't really dwell on it because I wanted you to just get your head around like I said, the idea of what we're trying to do. But what we're really trying to do is represent as a fraction how much of the product we have over the amount of reaction. And the way we do that is we take the product, the concentration of the product, we raise it to the power of the molar ratio, and we divide it by the concentration of the reactant. So we're going to do that now. The Kc value for this reaction is going to be equal to the concentration of hydrogen iodide. So I use square brackets to denote concentration. And I raise it to the power of 2 because it's it's 2 moles, isn't it, is produced from the equation. And then I divide that by the concentration of hydrogen, like so, multiplied by the concentration of iodine. Okay, so that's all it is. That's what Kc is. And believe it or not, there's often 6 or 9 marks going for this, not just at ordinary level, but at higher level. So it's really important that you can do this carefully, that you include the square brackets, that you remember that these are multiplied by each other and that they're raised to the molar ratio. Okay, there's easy marks available here, which are really, really important. Okay, so the next part of this question is to calculate the value of Kc. So we're going to do that now. Again, this is one of these things where if I just do a worked example, which I think it makes life a little bit easier. So I'm going to try and do that now. And to help us with that, what we do is we use a table. So I've drawn the table here. I'm going to show it to you now. Right, so here's the equation again. This is hydrogen. This is iodine. It's the same equation. You can see that, and I've just squashed the Kc into the corner because it's not really important because I've showed you what that is. Okay, so that's the exact same thing. And again, this is 2008 question B. But what I want you to do is have a look at this table. So in the table, we have columns for the reactants, hydrogen and iodine, and hydrogen iodide. And in the table here, we have the amount that's used at the start, the amount that's used up during the reaction, the amount that's present at equilibrium, and the concentration that's present at equilibrium. And we're always going to use this table when we do these kinds of questions, okay? Sometimes it's a little bit more long-winded than it needs to be, but it makes it less likely that we're going to make a mistake. So the first thing that I'm going to do is to fill in the values that were given in the question. So we're told that we started with 11 moles of hydrogen and 11 moles of iodine. Again, you can refer to this 2008 part B is the bit that I'm doing, okay? So at the start of this reaction, we had 11 moles of hydrogen and 11 moles of iodine. And the other piece of information we're told is that at equilibrium, we had 17 moles of hydrogen iodide, okay? So for the column that says equilibrium, I'm going to put in 17 there like that. That all right? So what I'm doing is I'm filling in the information that I've already been given so far in that question, right? Now, let's start to fill in the other boxes now. So at the start, for example, I know I had no hydrogen iodide, right? So at the start, we started with 11 moles of this and 11 moles of that, and we had 0 moles of that. So I'm going to fill in 0 there. Right, now, how much hydrogen and iodine got used up? Well, let's have a look. For every 2 moles of this that's produced, we're going to use 1 mole of hydrogen and 1 mole of iodine. So we know that we've produced 17 moles of hydrogen iodide. So the amount of moles of hydrogen and iodine that got used up is going to be 17 divided by 2, because the molar ratio is 1 to 2. Does that make sense? So 17 divided by 2, which is 8.5, is going to go in this column here, 8.5, and this column here, 8.5. Now, that's really, really important that you see where that goes, okay? That is not the concentration that's at equilibrium. That's the concentration that's been used up. So 8.5 moles of this and 8.5 moles of that have been converted into 17 moles of hydrogen iodide. So they're gone, okay? And the amount of hydrogen and the amount of iodine that's left behind is whatever we had at the start minus whatever got used up there. And that's what we're going to fill into these boxes here like this. That makes sense? So that's what we're going to do. We're going to subtract 8.5 from 11 and we get 2.5. And we're going to subtract 8.5 from 11 here and we get 2.5. So when the mixture reached equilibrium, the amount of hydrogen and the amount of iodine that were left from the initial 11 moles is 2.5 moles each. And the amount of moles of hydrogen iodide present is 17 moles. We know that because that was given to us in the equation. This box we don't need to fill in because obviously if there was none at the start, none can be used up. Okay, so you can leave that blank. Now, the final column here for equilibrium concentration. Sometimes in some of these questions, right, they mention that it was in 5 moles volume or 10 moles container or something like that. There's no mention of this in this question. This is a relatively easy one. That's why I picked it first. And that's why I wanted to do it. So actually there's no change here. We can assume that the concentration is the amount of moles. Okay, I'm going to do a more complicated one later and you can see where we have to adjust for this. But basically these numbers are going to be the same because we're dividing everything by 1. Okay, so we don't need to write anything there other than 2.5, 2.5 and 17. So now all I have to do is plug in these values into my equation that I got from KC. So the hydrogen iodide concentration at equilibrium is 17. So I'm going to put 17 squared, because I square it, remember? And I'm going to divide that by the, oh, that's wrong. That should be hydrogen. Sorry, I just realized I wrote that wrong. The hydrogen equation, the hydrogen concentration at equilibrium, and the iodine concentration at equilibrium. So these two values here, 2.5 and 2.5. So it's 2.5 multiplied by 2.5 like that. So what I'm going to do is I'm going to use my calculator to work out what this is. And the answer I get, 17 squared divided by 2.5 multiplied by 2.5 is 46.24. And in the end, that's what I get. There's no units because this is moles per litre squared and this is moles per litre and this is moles per litre, so they cancel each other out. So my answer for KC is 46.24. Okay, I don't want to go any further with that question today because that's all we've done so far. We don't need to worry about Le Chatelier yet. We'll do that later. I just want you to get the basic premise of how we do these questions. That's a relatively easy one. I'm going to do a slightly harder one next. Okay, hope that helps. Bye-bye.